So welcome back everyone to section and happy Valentine's Day today. So let's just take a look at where we are in the course right now. So today is the 14th. So we are right here in the class. So tomorrow you have your second mission, which is due. And hopefully everyone's been following along with the modules on the website and reading both the textbook and the materials we prepared for you online. How has this week gone? Does anyone have any questions about any of the material or any of the homework assignments? I saw that a lot of people were having some difficulties with R, but I'm glad we were able to clear that up last week. So this was the module that was covered in the past week, module 3, it's tested for on your assignment that's due tomorrow. If anyone has any questions, I'm happy to go through any questions on the lecture, or we can, I'm here basically here for you guys. So if you have any questions about the material or anything about R, we can go over some of the material tonight. If anyone has any questions, otherwise I can just go through some of the lecture material with you guys. So, so let's go over some of this lecture material. So we covered mean, median, and mode to describe the center and location of data. We also went over other measures of location, such as percentiles and quartiles. And we also talked about the variation or the spread of data, which we can represent by the range, the interquartile range, the variance or the standard deviation of the data. So here we talk about the mean, which we represent by x bar, and the calculation for the mean or the average here, which they're the same. Mean and average are interchangeable. So if you're finding the mean of a data set, we can just add all of the numbers together and then divide by the number of numbers in our set, and then we'll find what the mean or the average is. And when we're dealing with samples, in statistics, we're either dealing with a sample or a population. So there can be two variables representing both the sample and the population. So to represent the sample, we notate it with x bar to represent the mean. And for the population level, we use the Greek letter mu to represent the mean. So in statistics, when we are dealing with the population level, we're going to use Greek letters, and then for the sample, we're going to use regular English letters. So it's the same calculation for calculating the mean from a sample and the population. Just note that our notation is changing from x bar to mu and little n to big N to represent the population size. And there are pros and cons for using each of these different measures of so the mean, the advantages are it represents all the data points, and they're commonly used in statistical models and calculations. The disadvantage is it's sensitive to extreme values or outliers. So just to show that is if we add in an outlier, this 10, it will greatly impact the mean by increasing our average 1 point here between these two. And so this week we were dealing with the popularity data set, and we're looking at children. So as a child psychologist, we're looking at different variables amongst the school children here, and we can take the mean of the grades variable, which is just calculated like this. We can take the mean of the sports variable, looks, money, etc. And in this case, with the data set that we're using, a lower mean implies a higher ranking. So just be mindful of that, so that actually the closer it is to 1, the higher it's ranked, and the higher mean will be, yes. And Michael had a question about variance and standard deviation. So we can skip through this and get to variance and standard deviation. So just, we covered mean, median, and there's a difference between the two, and we also covered the mode. So these are used in different situations. So let's talk about spread. So just to set up to get to variance and standard deviation, what they represent is they're representing the spread of data. So just to introduce that concept, we can actually use the concept of quartiles, where if you actually take all your data and you look at the spread of the data, we can have different quartiles. We have the 25th percentile, the 50th percentile, which is also the median, the 75th percentile, and the 100th percentile. So this is one way of representing spread within your data. And there's another way of representing it, which would be the range as well. The range is just from the smallest number to the biggest number. And besides the IQR and the range, we could also use variance and standard deviation. So what it describes is spread amongst your data. So as we said, the range is just the difference between the smallest and the largest values, but it's not as informative. And then we can use the interquartile range, which is Q3, the 75th percentile, minus Q1, the 25th percentile, to get an IQR. And here, we're just going through the concept of, on a number line, we can actually find the distance from the mean. So here we're adding up all the differences from the mean for each sample in the set. So when you average the means, in this example, you got 0. So that means that there's, on the right side, positively, there's as much deviation than on the left side, negatively, as you can see here. So the average of all the distances from the mean will always equal 0. So as a measure of variability, that's useless. The solution is to square the differences so they're all non-negative and then take their average. And this is what's called the variance. So the variance is representative of the spread of your data. And the way we calculate it is we take the difference of each sample from the mean, and then we divide it by the sample size, and then we're going to square the distances so they're non-negative in order to get the variance. So, and that's shown here, how that works. So this is 2 points away from the mean, -2, but -2 is negative, and that wouldn't work. We just went through that. So we have to square all the differences. So that gives you a +9, +4. It's the same with this example. -1 squared is 1. And so when you add all of these differences together, then you can calculate the variance, which in this case, if you have if you have a difference of 1 on the right side 2 times and a difference of 1 2 times on the left side, you can add that up and get 4 as your variance. Here you have much more variance because, as you can see here, you have a 36 on the right side and 9 and 1 on the left side, so it's a 36 is variance. Here, as you can see, you have an equal amount on the right and the left. You have a 4 and a 1 and a 1 and a 4 on the left. So your variance is actually small. Your variance here is 2 because they're both equidistant on each side. And here the variance is even smaller because you have smaller numbers here. So basically what the variance is telling you is how spread apart your data is, how spread apart it is from the mean, the central value. So variance, because it's in squared units, we don't typically talk about variance that much in collective statistics. So we typically talk about standard deviation. And the reason for that is because standard deviation is the square root of the variance. And once we square root that, it actually goes back to the units that we're dealing with in the example. Because when we talk about variance, the units will be based on the units squared. So if you're dealing with inches and you're talking about the variance, it's gonna be inches squared, which is not what you want. You want inches. So what we do is take the square root of the variance to get the standard deviation. So in this example where we found the variance, for this example was 2, we can take the square root of that and get about 1.4 is the standard deviation, as you can see here. In this case, you have 0.8, and then if you square root that, we have 0.9. Here, the variance was 9.4. We could take the square root of that and get 3.07. So the standard deviation is 3.07, and it's a larger standard deviation than in this case because you can see there's more spread to the data. So the idea of standard deviation and variance, they're the same concept. First of all, they're representing spread in your data, and that's how we can understand what standard deviation is. It's the further away that the data is, like, from the mean, and the differences to the mean. So if you're comparing two data sets and one has a higher standard deviation than the other, that would mean that the one with the higher standard deviation will have much more variability to the data than the one with the lower standard deviation, which is probably closer to the mean. The differences are smaller from the mean, so they fall alongside the mean more. So defined, the variance is the average of the square distances or deviations from the sample mean. And because we're squaring the distances, the variance is always non-negative. The way we calculate variance differs slightly depending on whether we have a sample or population. So that's important because it's, let's take a look at this. For the population level, and just so we can go over the notation here. So whenever we're dealing with the population level, our notation is going to be in Greek letters. This is the Greek letter sigma squared, which means the variance of the population level. And here what this notation means is mu is the mean of the population, and x1, x2, etc. is going to be each individual point in your data set. So in order to calculate the variance of the population is we'll go through our list. You know, let's say you take it from smallest to largest in your data set, and you're going to subtract each one. You're going to take the sample point and you subtract the mean, square the difference, and you add it in for each different set in your data point, and you're going to divide that by n, which is your population size. And that's a large capital N because you're dealing with the population. For the sample, notice we're not using sigma squared, we're using s squared. And it's all the same here, x1 minus x bar. X bar is just representing the mean of the sample, except that we actually divide by n minus 1, which is called the degrees of freedom. So there's a small difference when you're calculating from the population level variance to the standard deviation, to the sample variance, because you're using this n minus 1 instead of capital N. So someone asked about explaining degrees of freedom. So the degrees of freedom is generally the sample statistics, and it's the difference between the sample size n. So in this case, you're doing n minus 1 for your degrees of freedom. So just know when you see degrees of freedom, in this case for calculating the standard deviation, you're going to use the n minus 1 for degrees of freedom. So here it says, because we're using the sample mean x bar in the final calculation of the sample variance, the degrees of freedom is n minus 1, whereas in the population, we had no other sample statistics used in the final calculation of the sample mean, so the degrees of freedom is n minus 0 equals n. But in this case, because we're using the sample mean x bar in the final calculation of the sample variance, the degrees of freedom is n minus 1. So for the mean, we don't need to use degrees of freedom, it's saying in the sample, because we don't have the sample statistics in the calculation. In the case with the variance, we actually are using the mean, the sample mean x bar in our calculation of the sample variance. So that's why we need to use n minus 1 for degrees of freedom. And that's the reason why we need to use degrees of freedom of n minus 1, because we're using the mean in the calculation of it, the sample mean x bar. Because there's basically because we have a constraint on one of the variables here, and this exercise is explaining that, because you can suppose that you have 3 numbers and you have a constraint that the mean is equal to 3, and you know that you can freely pick any 2 values, but the remaining value is constrained by the value of the sample mean. So let's say you pick the first number is 1 and the second number is 3. Well, since the mean is 3, the value of that final number must be 5 because you have to add them all up and divide it and get equal to 3. So it's saying that we know the sample mean and we can fill this in for the information we know, and then we can rearrange and solve for that here. So it's giving you an example of why we have to use degrees of freedom. So we can look at the variance of income in the United States, for instance, and here we say that the variance is equal to, this looks like $3,050,000,000. But the units of this value of the variance is in dollars squared, which does not make sense to us. So what we do is we take the square root of the variance and get the standard deviation. The way you get the standard deviation from a population, see we have the Greek letters here, sigma is equal to, just as we said before, it's the variance square rooted. So we just take the square root of the variance. And with the standard deviation from a sample, it's the same. It's the variance square root. And just remember that when you're dealing with variance or standard deviation of a sample, your denominator is going to have degrees of freedom n-1. So here we can see that by taking the square root, and we get $55,241 for the standard deviation of income. So if we square it, we would get the variance. They're interchangeable in that you can square root the variance to get the standard deviation, or you can square the standard deviation and get the variance. So this is just asking you some questions here. It's asking if your mean is $100 and your standard deviation is equal to $0, what is the spread of the data? And the answer is none, because the standard deviation is equal to 0. So that means there's no spread within the data. If you have a standard deviation of 1, that means that the overall spread of the data is small, because your sample standard deviation of 1 is a lot smaller than your mean of 100. So that means that there's very little variation in the data here. Again, if you increase it to 5, that's also small. If we increase it to 75, that will become median because it's more sizable to the mean. And if you have a standard deviation of 10,000 with a mean of 100, that's going to be a very large standard deviation. So this is just to illustrate the concept of standard deviation with spread. So if the standard deviation is larger than the mean, this suggests the data is spread out. If the standard deviation is smaller than the mean, this suggests that the data are concentrated around the mean value there. So in this interpretation with the income, we see that the mean income is $37,486 in the United States, and the standard deviation is $55,000. So since the standard deviation is larger than the mean, we can say there's a relatively large spread amount around the mean, which makes sense because the income of the United States, it varies widely, and there is a large spread of that data points. You have people who are making very little money, and then people who are making a lot of money, and there's a big spread amongst income in the United States. There's a large disparity, one could say. So, you might look at a country, let's say in Scandinavia or Europe, where people might have similar salaries across the board, across industries. They would probably have a smaller standard deviation than if you were to look at the standard deviation of income in the United States, since we have such big disparities amongst earners in the United States. So that's how we understand what standard deviation is and variance. So practically, when you're discussing statistics and you're discussing the spread of your data, you'll use the standard deviation to report that. We don't really typically talk about variance too much because the units are in squared values, so that doesn't really make too much sense as far as reporting useful statistics. So we typically use the square root of the variance, which is the standard deviation. So the idea behind variance, standard deviation, and also the interquartile range, and also just the range, is that we're all describing the spread of your data set. And like we said earlier, the mean and the median can be used to describe the center of your data, and the standard deviation will represent the spread of that data to show you how much variability there is. And so, and then the second part of this lecture went into visualizing data. So we can actually visualize how the data looks, and we can actually see in a visual format the mean and the standard deviation and how that looks here. So we have a few different ways of displaying data. We can use a dot plot. Each dot will represent a different statistic point in your data set. We can also use a stem and leaf plot. So this is where we're using a stem, which will be the first digit of each number, and then the leaves, where each of these will represent a different number within the set. So this can be read as 54, this one's 75, and so on. And so here we can see what the range is. We see the smallest value is 54 here, and the biggest number in the data set is 79. So, we could calculate what the range was pretty simply. And then we are looking at histograms. So histograms are used more frequently than, say, the other two. And what a histogram is it's a simple bar chart. So here we're showing how we can alter the number of bins in a histogram to give a different representation of that data. So here we have, and the bins are the number of charts, a number of rectangles here. So we see 1, 2, 3, 4, 5. This is 5 bins. If we reduce it to 3 bins, this is how it'll look. And if you increase it to 10 bins, this is how the same histogram will look. So it's important to realize that depending on your bin size, you might draw different conclusions from this data. As you can see here, with the increase in bins, we could see that these two bars are actually equal here, which you don't have the same resolution with either of these other two ones, but you'd still get the idea with the overall trend. As you see here, it's increasing right over here. So you have more instances of higher occurring numbers in this data set. And this is looking at life expectancy. So it makes sense. So one would say that the average life expectancy, because you have such high numbers here spread on the right, the average would probably be spread around here on the right. So your average might be somewhere around here. And that makes sense because there's few people who die very young, and you'd have much more people who are dying around the average, and then it kind of drops off because you have you have less people who are living to a longer age past the average age here. So this chart makes sense, and we can draw some conclusions from that. We can also look at a density plot, and the density plot will show us like this what the density of the same data is, and this is life expectancy. So it might give you a little bit more resolution as far as looking at these curves, and so it gives you more resolution as opposed to having those bars like you had earlier, so you can actually see the smoothness in the data. Another representative way of showing our data is a box plot, and the box plot is used really to show your range of your data because it's dealing with the quartiles Q1, Q2, Q3, and Q4, and it's showing you what the interquartile range is, which is Q3 minus Q1. So the way we read this box plot is this value will be the minimum. So this is actually truly the minimum of the data set, this dot here. However, what R recognizes is that this data point here is actually an outlier. So that's why it's represented by a dot, and it's not included in this whisker. So it's actually considered an outlier. And there's a calculation to calculate what the outliers are, and we'll go over that. So this is an outlier. This is the smallest observation that's not an outlier. This, for the box, represent Q1. This is going to represent your median, your 50th percentile, and this will be the Q3, the 75th percentile, and this represents your maximum. So as we can see, this is the life expectancy data. So as we said before, it's skewed here to the right, as you can see. And this is an outlier. This represents Haiti in the life expectancy data. So we can understand that Haiti might have a lower life expectancy compared to the other countries on the global level. So in order to detect outliers, we can use the box plot rule, which is a calculation. A value is considered an outlier if it is less than the Q1 minus 1.5 times the interquartile range, or greater than Q3, the 75 percentile, plus 1.5 times the IQR, the interquartile range. So if there's any numbers in your data that are either below the Q1 minus 1.5 times the IQR, or vice versa on the other side, above the Q3 plus 1.5 times the IQR, those are considered outliers, and we can represent them by a dot, like R does. If you use some other programs, it might represent those outliers differently by a star or something, but R uses a dot. So we have one outlier here, and this is how the rest of the box plot looks like. And then we could talk about skewness. So skewness is related to the concept of outliers. And if a data set is skewed, then a numerical summary such as the mean can be highly misleading because you're dealing with skewness. So sometimes with skewed data, we'll use the median over the mean because the mean is so sensitive to skewness and outliers. So this is what we're talking about when we're talking about skewness. So this is symmetric data, and the mean, the median, and the mode will all be the same in the center of the distribution because we have a symmetric distribution. If we have a data set that's skewed right, you'll see here from visually what that would look like. And we'll find that the mean is actually greater than the median and it's greater than the mode. So you'll find that the mean is greater than the median. That's representative of skewed right data. If you have the mean being less than the median, that's representative of skewed left data. And here we can see this is where the mode is, the most commonly occurring occurrence in the data set is. We can also talk about different modality of distribution. So they can have multiple peaks. If you have one clear defined peak, we could say that's unimodal. If there are two apparent peaks, then we could say that's bimodal. And if a distribution has two or more peaks, then we could say it's multimodal. So here, looking back at the life expectancy, we can say this is left skewed. So our mode would be somewhere around here. And the tail is on the left, which is pulling down the mean relative to the median. And this is considered a unimodal data set. You can also look at the distribution of GNP per capita. So the distribution of GNP per capita is right skewed. As you can see here, there's a long tail to the right, and the tail is on the right, which is pulling the mean up relative to the median. And this is a slightly bimodal distribution. You can see here that you have a clear peak here and a second developing smaller peak right over here. Talk about distribution of population growth. And if you look at this, we could say this is roughly symmetric with some slight right skew. And the mean is greater than the median, but not substantially. And this is slightly bimodal, as you can see here, there's two peaks. So that was the visual representation of the different ways we could display data. So the big takeaways here, we're learning about how to summarize our data using mean, median, and mode to represent the center. We also learned how to represent spreadness within the data using the range, the interquartile range, the variance, and the standard deviation. And finally, to wrap it all up, we learned about how to represent our data visually with these different plots. We learned about the dot plot, we learned about the stem and leaf plot, and we learned about the histogram. So that was what was covered in this lecture. Does anyone have any questions on this material that we can go over together? So Michael has a question. What's the difference between a histogram and a bar graph? So they're the same. They're interchangeable. The technical term for it is a histogram, but a bar graph is what's used colloquially. But they're the exact same, to answer your question. And then you have a box plot. This is a box plot. So the box plot is representing the spread in your data. So again, we can go over the box plot because this sometimes can be tricky if you haven't seen this before. This will represent the minimum, this whisker here. This one will represent the maximum. This solid line on the box will represent the Q1 of the data, the 25 percentile range. And this will be the median, the 50 percentile. And this Q3 is the 75th percentile. And when we talk about the IQR, it's simply this Q3 minus the Q1. So this is representative of the 50%, the middle 50% of your data, and that would be the IQR is the 75th percentile minus the 25th percentile. So here it's a way to visually look at the spread of our data. And we learned about how to detect outliers using the calculation here and skewness. So when we typically talk about the income in the United States, we typically report a median value because there is so much skewness in the data that a mean is typically not that informative of the United States income because we have very, very, very high earners that can distort the mean, and the mean is very sensitive to outliers. So because there's so many outliers, we typically report the median income in the United States, which is a more accurate representation of the middle income of the center of the spread. So Fatima had a question, are the formulas something we'd be expected to recall? So for exams, we're basically giving you an open book exam. So it would be good to be familiar with the formulas and be able to use them so that you're comfortable finding your answers with the formulas. But as far as if you're going to be tested on memorizing them or not, you're going to have your notes available to you. So if you want to make a formula sheet, you can, so that you have all those formulas available to you. So it's good to be familiar with how to use these formulas, and if you can memorize them, that's great. Something like calculating the mean, can become very secondhand if you're familiar with the formula and you practice with it on problems. So something like the standard deviation, it might be a little bit more difficult to remember the entire formula, but it's good to be able to know how to use it and understand how the formula has been come up with, so that it's easier for you to run these calculations, understand what they mean. So I hope that answers your question. So in here, we can look at R. What other things should we focus on as we go through the modules? Fatima asks. Yeah, so I'd pay attention to some of the big takeaways. So the formulas are good, so you should be able to be comfortable using the formulas. And I'd also be able to, I'd focus on learning when each of these formulas are used and what they represent. So it's good to know that standard deviation is representing the spread of your data. And if you want to look at the mean of your data, the center of your data, you would use something like the mean or the median. It's also good to know, when you would use the mean or when you would use the median, one over the other. So, I guess there's some key takeaways in some of these lectures that maybe you can try to focus on. Trying to, all these different terms that we're going to be using. It's always good to maybe have a formula sheet like we spoke about, where you're putting down, when you learn a new formula like the mean, you can put that down and be able to understand when we use the mean and why we use the mean and when do we use it over a different measure like the median, and also be able to understand what the median is and how to use that and whatnot. So I'd say for each formula, you can you can write down your formula sheet and be able to understand why we use it and when we use it. So for this next problem set that you have that's due, we're using the popular kids data set. So as you see here, we have these different categories. There's 478 students in this data set, and they range from ages 11, so we can sort by the age and take a look at that. So we see here that the youngest student is 7 in this data set, and we can look at what the highest is, which is age 13, and they're in grades 6 through 4, I believe, right, 4. And then we're giving you also some other information about the students, what school they go to, whether their school is located in an urban, rural, or suburban neighborhood. And the idea of this study was they were looking at whether grades or being popular or sports are most important to these different students. So they were asked to rate how important each of these things are to them as students from 1 to 4, with 1 being the most important thing to them and 4 being the least important thing. So this is the data set that we're dealing with this week. And remember, you're always going to want to make sure that your Mosaic package is checked off when you're working with R. So you just check off the Mosaic package here, and that will load up the Mosaic data set. And then once you've done that, then you can just go through the R codes, which we give you here. So this is a good command. This will run summary statistics on our data set. So we can run that. Let's see here, and this is looking at the grades variable. So amongst the grades, we see that the minimum is 1 and maximum is 4, which we were saying. The median is 3 for grades. So overall, it seems like the grades are, since the median is 3, and the mean is about 2.6, you could say that it's less important than some of these other categories to the students. And you can see here that the standard deviation is about 1, so that gives you an idea of what the spread is. And then we can actually, if we wanted to look at a different variable, instead of grades, we could just change it to another variable. So say we were looking at the age and we wanted to know the summary statistics for the age. What I can just do is, instead of grades here, I can write age, and I'll bring up age distribution here. So we see that the minimum is 7, the maximum is 13, like we said, the median is 11, the mean is 10.4, the standard deviation is a little less than 1. So that gives you an idea of the spread of both the center and the spread of this data. And some other commands we can use. We can use the variance command and the standard deviation command, which are just var and sd respectively. And as you can see here, for the commands, we're putting in the variable that we're interested in first, and then we're telling R which data set we're using by having data equals popular kids to let R know which data set we're working with here. And this will show us that the square root of the variance is equal to the standard deviation for the grades variable. So we took the square root of the variance of the grades and we got 1.08, which is equal to the standard deviation. So, you know, we can show it that we can look at the variance, which is 1.16, and if we take the square root of 1.16, we'll get the standard deviation, which is 1.08. If we want to find the range and the IQR of a numerical variable, we can use the range and the IQR commands. The range for the grades we said was 1 to 4, and the IQR was 2. And here we give you some formulas, some code on how to display our data so we can make different graphs. So we can use, we can make a histogram of the ages here by using the histogram tool, and the n int equals represents the bin size. So we can make a histogram with 3 bins, or we could change this 3 to a 5, make a histogram with 5 bins, or we could change it to 10 and make a histogram with 10 bins, and we can see how that looks as we increase the number of bins here. We could also make a density plot using the density plot command. So the density plot looks like for age. So as we can see here, the mode for age looks to be 11. That there's about the most commonly occurring age in this data set is 11 years old. And here we can make a box plot. So BW plot will make a box plot. So this will be running a box plot on the age variable. So we can see here. So actually they can, so if we use the outlier rule, it looks like both ages 13 and 7 are considered to be outliers. That's what R is showing us by having these empty dots represent 13 and 7. So these are the maximum and the minimum values respectively within the data set, but because they were considered outliers, we actually look here at the dotted line to find what the minimum and maximum non-outlier instances. So here we could say the minimum non-outlier is age 9, the maximum is age 12. If we're looking at the Q1, we can see that's 10 years old here. If we're looking at the Q3, that's 11. And so this is also interesting as well. So this box plot, some people might be confused here because we're saying here that the Q3 is 11, but also the median is 11 as well, which is what this is showing us by having the dot here. So that's confusing. You might ask, how can 11 be both the 50th and the 75th percentile? But in the context of this data set, that's actually what the case is, and actually that's how the data is displayed. So don't be confused if you see that if you see something like this with the median being the Q3, it's possible. And here we can run some fave stats here. So, you know, as we were saying, once you run the code, you can see both the median and the Q3 are the same. They're both 11. And we can create a stem and leaf plot. This will create a stem and leaf plot. You have to create a random sample. So, you know, this will take a random sample of 25 students from this population. And we're gonna, so this is telling R to make a sample of 25 students from the popular kids data set and storing this as a new variable, which we're calling popular kids 25. And then we can view that. So let's run that command and see that. So as we see here, we created a new sample. We can observe this is the 25 students, and now we can create a stem and leaf plot. So I think there's a mistake here. Instead of popular kids 10, it should be popular kids 25. So this would be how we can make a stem and leaf plot from those 25 students. So it took those random 25 students, and here is what a stem and leaf plot would look like. Here, the numbers were from 1 to 4, so you can see here that 2 was the most likely, most occurring choice for the popular kids set here. And to create a dot plot, we can use this command, dot plot. This shows the dot plot. So, you know, a dot plot is it's pretty similar to the idea of a histogram, except that the dot plot will show you each and every instance here, whereas the histogram doesn't show you that. But the histogram is filled in with the solid boxes. Will give you an idea of the similarities and the differences between the dot plot and the histogram. So does anyone have any other questions? So I think just be mindful about the numbers. Like we said, the 1 is what they're rating the most important, and the 4 is what's least important. So that's an important tidbit of information to remember from the lecture. So I'd say if you've gone through all the modules and if this made sense to you and the lecture made sense to you, I think you're in good shape to complete the assignment by tomorrow's deadline. If you're still unsure about some of this, you can review it, and feel free to let us know if you have any questions. Happy to answer any questions now if anyone has any, or feel free to send us an email or post on the discussion board. So Fatima had a question, the difference between median and the mean and its relation to standard deviation and variance. Okay. So this is the mean, the average. What we're doing is we're calculating the mean by summing up each instance in your data set and dividing by the number of data points in your set so that you can find the mean, which will represent the central value in your data set. So the median, what the median is, and just so we know about the mean, it's sensitive to extreme values or outliers. That's the disadvantage to the mean, but it is representative of all data points, and it's used most commonly in statistics. So we'll typically use the mean to represent the center point of data that is symmetrical, so that if there's not much skewness, the mean is the best measure to describe your center of your data set. The median is the 50th percentile, which will show you the middle number. And the way we can calculate that is if we have an odd number of observations in our sample size, it's just the middle number. And if it's an even number, we'll take the average of the two middle numbers to arrive at our median. So just to calculate the median, if we have 5, 10, 43, 15, 100, the median is 43 because this is an odd number and we're just looking at the middle number. In this case, we have an even number, 5, 10, 43, and 50. So we take the two middle numbers, 10 and 43, take the average of that, which is 26.5. So when we use the median, the advantage of the median is it's not affected by extreme values, and it makes intuitive sense to say half or above and half below this number, but it's not used very often in statistical models. So the median is good to use when you have skewed data or you have data with a lot of outliers to represent your center of your data, because the mean is very sensitive to these to the skewness of a data set or the outliers. You'll typically use the mean for more symmetric data and the median for more skewed or more or data with a lot of outliers to give the middle to give the center of a data to describe the center. So here we can look at the mean and the median. So, with our data set that we just looked at, the medians are all whole numbers because we didn't deal with any decimal points for the self-rating study, but the mean can be decimals, right? So this could be a more accurate description if you don't have skewness. So we see here sports is 2.09, the median is 2. So they're similar, but here you actually can't differentiate between looks and sports as far as the median is concerned because they're both 2. But if you take the mean, you'll notice that the looks is slightly larger than the sports category, which means you can make a slight judgment call as far as which ones are more important. But just to show with the outliers, if you made a mistake and typed in a large number, that would greatly affect your mean. You see, before it was 2 and now it's 2,000 is what your mean is. But if you were taking a look at the median, it would be unchanged because the largest number is going to be the largest number and your median is going to be the same regardless if you made that mistake or not. So as far as the relation to the standard deviation and variance is concerned is the mean and the median is going to represent the center of your data, and the standard deviation, the variance, will represent the spread of the data. And we said here when we were talking about standard deviation is we can compare the standard deviation to the mean to give an idea of whether the data is very spread out or not. So if the standard deviation is larger than the mean, this suggests that the data is spread out, that there's a lot of variability. If it's smaller than the mean, it means it's more centered around the central, the mean of the data set. Does that answer your question? Does that make sense, Fatima? Great. Well, good luck on the assignment if you haven't completed it yet. And I'll be back on tomorrow at the same time in case everyone has any questions, and we can continue the conversation then. And if I don't see you tomorrow, have a great week, and we'll be back next week.